Assalamu alaikum wa rahmatullahi wa barakatuh. I hope you are having a good day. My name is Muhammad Hayyan Sibai. I'm member of Faculty of Engineering Technology, and I'm here to participate in our Mooc course, which is Circuit Analysis Power Consumption. Now I'm going to start with you part 2 of Module 10, which is Introduction to Basic AC Fundamentals. By the end of this part, you are going to be familiar with the frequency, period, amplitude, and peak values, the angular and graphic relation for sine waves, and voltage and currents as function of time. In the previous part, we saw how the generator is rotating, and the output of this generator is actually the sinusoidal waveform. As any waveform, it has some characteristics or aspects. They can be summarized as frequency, period, amplitude, and peak values. So, as you maybe already know, frequency is the number of cycles per second of a waveform. So, for example, if we say that this waveform is 1 Hertz, that means it gives 1 cycle per second. As you can see in the graphs here, if we have 1 cycle per second, so it's this waveform, we can say it is 1 Hertz waveform. If we have 2 cycles, it's 2 Hertz. And most of the AC generators actually are producing 60 cycles per second, which is 60 Hertz. So if you look at any electrical plug, you see it's like 60 Hertz. One other things related to the frequency actually is the period T, which a period of a waveform is the duration of 1 cycle, and it's actually the inverse of the frequency. So the period actually can be measured between any 2 corresponding points. So as you can see, it can be between 2 zeros, or between 2 peaks, or between any starting point until the waveform is returning back to the same point. Other concepts or characteristics of the waveform is the amplitude. Amplitude, EM, VM, or as we will see later for the current IM of a sine waveform, is the distance from its average to its peak. There's also what's called the peak-to-peak value, which is measured between peak and between the peak and the trough values of a waveform. Third one, which is important also, is called the peak value. So the peak value of a voltage or current is its maximum value with respect to 0. So we need actually to differentiate between the peak value and the amplitude value. The amplitude value, as you see, it's from the average to peak. The peak value is from 0 to peak. So as you can see, the difference between A and B, in A, EM and EB are the same. So the amplitude and the peak value are the same. But in the second one, when we have actually 2 sources of voltage inside the circuit, so as you can see, the EM, the E equal to EM plus EB, because EM is from the average, which is E, and the peak is from 0 to peak or maximum. Now we need to introduce another concept. We need to study the relation between angular and graphic relation for the sine waveform. Any basic sine wave actually has this equation: E equal to EM sine alpha, where EM is actually the maximum coil voltage and alpha is the instantaneous angular position of the coil. So as you see, it's like a rotating coil which is generating the sinusoidal waveform. So alpha is the position of the coil, and EM is the maximum value that this of voltage that this generator is generating. Another important concept we need to use actually in our lectures is the angular velocity. The rate at which the generator coil rotates is called the angular velocity. For example, if the coil rotates through an angle of 30 degrees in 1 second, for its angular velocity is 30 degrees per second. So the relation between alpha and time is actually dependent on the angular velocity. So alpha equal to omega t. Omega is the angular velocity. So expression of t and omega can now be found. T equal to alpha divided by omega, and omega is alpha divided by t. Let's have one example to understand more. So let's say we have a coil, as you can see here in the figure. This coil rotates at omega equal to 300 degrees per second. How long does it take to complete one revolution or one cycle? Solution simply, one revolution is 160 degrees because it's one cycle, so 360 degrees. So the time for completing one cycle, that means to complete 360 degrees. So we need 360 degrees divided by the angular velocity, which is 300 degrees per second. The result is 1.2 seconds. And since it's one cycle, that means it's one period. So we can use t, capital letter. So t, the period is 1.2 seconds. I give you this example as self-training. So now let's say we have a coil rotates at 3,600 rounds per minute. You need to determine its angular velocity omega in degrees per second. I give you the answer for make it easy for you. So the answer will be 21,600 degrees per second. I think it's easy for you to calculate this result. Now, one important thing also to know that normally angular velocity is expressed in radians per second, not in degrees per second. So you need to understand the relation because in some references you will find it's given by radian per second. So 2 pi radian is 360 degrees. So if we want to convert between radians and degree, alpha in radians equal to pi divided by 180 multiplied by alpha in degrees. For alpha in degrees, it's 180 degree divided by pi multiplied by the angle in radians alpha. 1 radian actually is 360 degree divided by 2 pi, which is almost 57.296 degree. These are some famous angles. So for example, it's easy to remember them. So 30 degree is pi divided by 6, and go through the table until 360 is 2 pi. Now, actually, why we introduce the omega or the angular velocity? Actually, because when we study the electricity, we don't care actually about the angle. We don't care about the angle of the generator. What we need actually to learn is actually our voltage or current at specific time. So we need to know the relation between omega, t, and f as a beginning. Let's say when alpha is 360 degree or 2 pi radian, t in this case is t capital, which is the one period. So if we use this concept, alpha equal to omega t, that means omega multiplied by t capital letter, which is the period, equal to 2 pi radian. Omega equal to 2 pi divided by t, which is radian per second. So this is the relation between omega and period. Similarly, if we take the inverse of period, which is frequency, so omega equal to 2 pi f. So from this logic, we can find the relation between omega, the angular velocity, and the frequency. Because most of the plugs, the electrical things will give you the frequency, will not give you the omega. So you need to calculate omega by yourself. Now, to find the relation between sinusoidal voltage and current as a function of time, we replace alpha equal to omega t in the sinusoidal equation. So we know the sinusoidal equation is E equal to Em sine alpha. Replace alpha with omega t, we get E equal to Em sine omega t. And similarly, we get V equal to Vm sine omega t and I equal to Im sine omega t. Actually, this is what we care more about when we're studying the AC. We need to know the voltage or the current at a specific time, not at the position of the rotator. Now, another important thing. So let's say when you start any experiment or starting any device, it's not necessarily that the voltage at this starting time is 0, because it might be any value, because it's like continuously change by time. So if a sine wave doesn't pass through 0 at time equal to 0, that means at initial time, so that means it has what's called a phase shift. So, and waveform may be shifted to left or to right. To express this mathematically, we add plus or minus theta to our equation. So in first one, when V equal to Vm sine omega t plus theta, this is the waveform is shifted left. In the second one, V equal to Vm sine omega t minus theta, and we say that the waveform is shifted right, as you can see also in the graphs. So it's shifted left or right. Actually, in electricity, we don't really work a lot in sinusoidal waveform. That's why we will use another concept, which is called the phasor. I just give you the definition of phasor now, and later on in part 3 of this module, I will explain more about the phasor. So the phasor actually is a rotating vector whose projection on a vertical axis can be used to represent a sinusoidal sinusoidally varying quantities. So as you can see in the figure here, we have the vector Vm. Rotating this vector, the output of it is the sinusoidal waveform. I will explain more about this concept later in part 3 of this module. So as a summary, in this part, we study the frequency, period, amplitude, and peak value as characteristics of the AC, which is sinusoidal waveform. Also, we understand the angular and graphic relations for sine waves. We see the voltage and currents as function of time. So we move from the angular or the angles domain to the time domain, which is more important for us when studying the AC. Thank you very much, and I hope it's not very difficult to understand the concept of AC. In this slide, you can see some references for more reading. Thank you very much.